Hey everyone, this is Verchke going over section 7A. We're going to do some chapter 7 sections, chapter 7A, 7B, and then maybe 7E. So we're going to keep it pretty crank and grind. The unit is over probability. It's a real good material, can help you in everyday life, and it's something I taught a number of times and feel fairly comfortable with. So what is probability? Here, let me change my pen size. Ooh, style of pen, just regular pen. Probability is not a percentage. Probability. Sorry. Spelling is not my strength. I was in special spelling when I was a kid. Well, anyway, a lot of people say, like, I have a 10% chance. That's not the probability. Probability, when you say there's a 10% chance, is going to be the decimal version of the percent. They also say, like, I'm rolling a die. You know, we can think of it as a die. And there's 6 sides, and the probability of rolling a 1 is 1 chance out of 6. But probability of this will be 1/6, which is a decimal. You know, we can probably go 1 divided by 6, and we get 0.16 repeating. We don't say 16.6%. We say the probability is the number 1/6 or 0.16 repeating. Now, the probability of rolling a 7, when you got a 6-sided die, and there's no number 7 on the die, you have 0 chances out of 6, which is 0. Or I could ask another really weird question. The probability of rolling a number between 1 and 6. Any of the numbers, 6 out of 6, which is 1. So, probability of an event. So, the probability of an event is less than or equal to 1 and greater than or equal to 0. Probability 0 means it cannot happen. Probability 1 means it's certain to happen. Now, part of the trick to calculating the probability of an event, and sometimes they say the probability of event A, where A is an event, so it's shorter, is the number of ways A can happen divided by the total number of ways. Now, when you're trying to figure this out and this out, sometimes it can get a little complicated. So we have ways to actually help us figure things out. For example, coin flipping. I can get, on the first toss, I can get a head or a tail. Then on the next toss, I can get a head, a tail, a head, or a tail. Then on the next toss, I can get a head, a tail, a head, a tail, a head, a tail, a head, a tail. And look, you can get a head, 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 a head, head, tail, a head, tail, head, a head, tail, tail, a tail, head, head, a tail, head, tail, a tail, tail, head, and a tail, tail, tail. Total number of ways is 8. But the secret is I use a tree to help me. First flip, second flip, third flip, because I struggle a little bit and this tree helps me. Now, my question would be, what is the probability of at least 2 heads? Then you go, well, there's 3, there's 2, there's 2, there's 2, 4 out of 8, which is 1/2, which is 0.50. You want to say 50%, but you don't because probability is 0.50. You can think 50% if you want. So coin flipping, and also the same with having babies. You can have a boy, girl, a boy, girl, boy, girl, boy, girl. If you have 3 kids in your family, just change the H's to B's and the T's to girls, and you got the same type of problem. So like a boy-girl problem, you can definitely draw yourself a tree. Now, you can also work with dice problems, and I'm trying to figure it out, and I think I already kind of discussed it. But let's work another die problem. Because it only has 6 sides, we know it's out of 6. So sometimes doing probability is kind of easy because it's just kind of obvious. Well, there's only 6 choices. But what is the probability of a 5 or greater? Well, you know 5 or greater is just the fancy way to say a 5 or a 6. And there's only 1 5 and there's 1 6, so there's 2 6, 1/3. Now, I must tell you, I was not a natural at probability. And the reason why is deck of cards. There's 52 cards. There's the aces, the 2s, the 3s, the jack, queen, kings, 13 different types of cards. There's 4 suits, there's the hearts, there's the diamonds, there's the spades, and there's the clovers or clubs. And I probably just drew a really bad club. And by the way, these are black, and these are red, these are black, and these are red. Some of you play a lot of cards, some of you probably never even touched a deck of cards. But when you start asking me probability questions over this, they can get wicked really quick. Now, if you give me 1 card, what's the probability of drawing a jack? Well, there's 2 ways to look at this. There's, well, 13 different types, 13 types, ace through 10, then it goes jack, queen, king. Sorry about forgetting the 10 there. But you could say, well, there's 4 jacks, jack of heart, jack of diamond, jack of spades, jack of clubs, out of 52. But then you could have just looked at it like this. There's really only 13 different types, and I pick one of them. And if we reduce that, it ends up being 1/13. that can get a little tricky because sometimes there's more than one way to look at a problem, and that's what's going to make probability a little challenging. And it always seems like no matter how many examples I do, people still going to struggle even when I'm done here. Now, I could do another one here. What's the probability of drawing a spade? Black card. Well, here's the deal. There's 13 spades because there's 13 ace of spades, two of spades out of 52. But you know what? You could say there's only 4 suits, and a spade is 1 out of 4 of them. Once again, 2 ways to look at it, making it challenging. I'm a little better at the 13 out of 52 personally. I really like it that you could reason out it's 1 out of 4, but that's up to you. Now, what we're going to do next is there's certain laws that govern probability, and one of them is called the multiplication principle. So, before I do this, I'm going to just make up an example and kind of show you how it works, and then I'll give you the fancy, book equation for this. So I wish I wouldn't have said so. But I got to put on here, I got 5 hats. I got 6 shirts. I got 4 pairs of pants. Oops. And I got 3 pairs of shoes. Now, assuming that's all I put on, that's all I'm putting on, how many different outfits do I have? Well, what they're going to say is, here's the event of putting your hat on. There's 5 of them. You got 6 different shirts. You got 4 pairs of pants. And you got 3 pairs of shoes. And there are 30, 90 times 4, 360 ways to dress. This is the multiplication principle. What it says is, suppose you have M outcomes for process 1. And N outcomes for process 2. Then total number of processes is M times N. And since it's called the multiplication principle, you just have to believe it. Trust me, really smart people worked on this, even though it seems simple, this all had to be proven. So when you're in a situation like this, when you're getting dressed, and you got 5 hats, 6 shirts, 4 pairs of pants, and 3 pairs of shoes, there are 360 ways to get dressed. I'm not saying they're all going to look good, only probably a couple. But that can be the question. But that's how you count. Now I already went over the tree because those trees get wicked. And if I had a 4th coin flip or a 4th child in the family, you know I'd have to extend that tree another level, and you're going to get 16 different things. So when I was drawing that tree, there was two choices for the first kid. And guess what? There's two choices for the second kid. And guess what? There's two choices for the third kid. And I know I did coin flipping last time, but technically this could be boy and this could be girl. And then you go boy, girl, B, G, B, G, B, G, B, G. And then we write them all down. But here's the thing. Event 1 is having a boy or a girl. Event 2 is having a boy or a girl. Event 3, or process 3, is having a boy and a girl. 2 times 2 times 2 is 8 via the multiplication principle. So I knew right from the beginning there was going to be 8 things. But, hey, you can't beat the tree. Tree wins over the multiplication principle, if you ask me. Next, we have the relative frequency process. This time, I'm going to do it in opposite format. I'm going to write down step 1, repeat, or let's not even get or, repeat a process many times and count number of times the event occurs. Step 2, probability of an A or an event is number of times A occurred divided by total number of times or observations. Now, this is more real life. So what they say is, and this is a problem, it's example 6 in the book, page 432, section 7a. It talks about geological records that a river has crested above a particular high flood level 4 times in the past 2,000 years. So it happened only 4 times in 2,000 years. It's a real situation. It's a event, and it's over a number of times, observation. So you observed each year. So that's all they're saying. And by the way, it's 1 out of 500. So this isn't so bad. Now, there's theoretical and there's experimental. Like, let's say you have, this is example 7, right out of the notes. It's called the fair coin test. And you got 2 coins. Obviously head or tail on both sides. Suppose you toss 2 coins 100 times and observe the following. Tail, tail, 22. 1 head. So that means tail, head, or head, tail, 51 times. And head, head, 27 times. So, bottom line, if somebody said, what is the probability of a head-head using the relative frequency method, meaning experimental, we were doing an experiment, it would be 27 out of 100 because these add to 100. But if you were tossing two coins, we know theoretically oops, sorry, other way around. The probability here, I can't spell it. Probability theoretically, okay, it's not happening. Of a head-head is 1 out of 4, which is 0.25. 0.27. Sorry about that. So if you're gambling, I bet you wish you were betting on head-head because it happened more often than it theoretically was supposed to happen. And that's, why people gamble. So they use a pretty cool approach in the book. I think what I'm going to do is instead of getting all fancy and using, oh, excuse me, I got another phone call. Pause. I'm back. Here we go. It's one of you guys. So, hey, by the way, don't be afraid to call me. I find it very enjoyable actually helping people. So, and don't email me a lot because I get a lot of emails and I always leave my telephone number, so don't be afraid to text me and I'll try to get to you. Right now, my schedule is pretty wide open. That's why I'm lecturing here and technically redoing this lecture to match this textbook and not the old textbook. Anyway, let's go to this. They actually say it, and they wrote the word, so they go theoretical. There's theoretical probability. There's relative frequency, which we were just talking about, real world things. And there's subjective probability. So there's 3 types. And subjective could be, I'm certain that you will be happy. You will, oh my God, I haven't spelled that word ever. Be happy with this car. How certain are you? Well, maybe this person is 75% certain. How do you know what level of certainty you are that people always say that? I'm 70% sure or 75% sure that you'll be happy with this car. Therefore, the probability of this car buying stuff is 0.75. That's all subjective means. Not a big fan. I love relative frequency because if somebody's willing to do experiment and put my data in the table, I just look stuff up and get answers. The hard one probably is theoretical. That's the math one, and that's probably why we're in the class, is to learn the theoretical one. Now, you will find that there's this classic problem. You guys are persistent. So, when you play Monopoly, you can roll a 1, a 2, a 3, a 4, a 5, or a 6. or the game of craps if you're into gambling. And then on the other die, you can roll a 1, a 2, a 3, a 4, or a 5, or a 6. Now, in both games, craps, which is gambling game, where it's a big long table and you're trying to roll 7s or 11s and they're yelling out all crazy stuff. Well, if you're going to play those games, it would be best that you actually understand the probability first. Now, in these games, you're always 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 1 is 3, and then you got yourself some really cool kind of math. The table fills itself out pretty slick. 9, 9, 9, 9, 10, 10, 10, 11, 11, 12. Now, somebody's going to ask you, well, how many different ways can you roll 2 dice? And the multiplication principle says there's 6 ways to roll 1 dice, and then the other event is 6 ways to roll another die, so 36. But the beautiful thing about the table is I can see all 36 ways. Here they are. So what is the probability of rolling an 11? Well, clearly, it's out of 36. And I can see there's two 11s, so 1/18th. Or give it a decimal approximation, depending on what MML says. Now, what they're going to do to you is they're going to ask for the probability of a sum less than 10, which it means probability 2 through 9. Now, you're like, wait a minute, all these? That's a lot of things to count, because there's only 6 things that aren't. So what I'm thinking, I'm going to just go, I know the maximum probability is 1, but I'm going to go 1 minus 6 out of 36, which 1 is really 36 out of 36. So there's 30 out of 36. I'm going to sneak up from behind. So the nice thing about probability, and also the bad thing about probability, is you can work the problem from the opposite way, ask the opposite question, and go 1 minus it. It's a really cool thing to have. So the probability of an event is 1 minus the probability of not the event. And that is what makes probability pretty interesting. So the probability of not event equals 1 minus the probability of the event, which allows us to have a really good like a second way to work a problem, especially when it comes to counting. Like, I don't want to count 30 things. I want to count 6. And then to go 1 minus the 6 out of 36. It's going to be a lot better, especially if you're playing cards. Like if you're playing poker. So poker, you get 5 cards, and they deal them to you. How many different poker hands are there? Well, there's 2,598,960 different poker hands. So that's a lot of counting to do if somebody asks me a question. So I'm going to want to think of a way to avoid some of the counting. So to sneak up from a problem from behind, hey, I'll take any help I can get. So that's a pretty awesome thing to have. Now, one last topic. I know this lecture is getting long, but we want to talk about probability Probabil. This is the second time tonight. Probability distributions. Now, typically, when they mention probability distributions, I have 3 whole sections to learn about it. But here we go. We're gonna do this up. So remember the earlier in the lecture, the head, tail, head, where I flipped 3 coins. And I have, let's see if I can do it without looking. The head, head, the head, tail. This is going to be hard. The head, head, the head, tail, the tail, head, the tail, head, the tail, head, tail, and the tail. Woo! That hurt. 1, 2, 3, 4, 5, 6, 7, 8. Now, so let's create an event. Let's go with 3 heads. 1 chance out of 8.125. 2 heads. 1, 2, 3. 3 out of 8.375. 1 head. 1 head, 1 head, 1 head. 3 out of 8.375. 0 heads, and a fancy way of saying 0 heads is 3 tails. 1 out of 8.125. Then what they do, so they're like clumping a problem. So they're just breaking it down into different, just kind of a different way to look at it, but people do want to know the probability of 3 heads, the probability of 2 heads, the probability of 1 head, the probability of 0 heads. But when they do it like this, what they do is they break this up into a histogram, like 0 heads, 1 head, 2 head, 3 head. And let's give a certain height to the 0.125. And then 1 head is 0.375, so 3 times bigger. 2 heads is 0.375. And once again, 3 heads is 0.125. This is called the probability distribution. It's a good way to look at the data. So you get 8 pieces of data, and then you kind of restructure it to look at it a different way. But you get your probabilities, and then you make a probability distribution, which is just basically a nice way to visually see your data. And it's related to probability, and the areas add up to 1. So the probability of event is between 0 and 1. But also, when you kind of break it up into this, if you add up all the areas, it's 1. Or if you add up these 4 numbers, it's 1. Obviously, it's more complicated than that, but, you know, that's the way it is. Now, unfortunately, they mentioned it, which means we're going to have to do some. So, you know, as I said, when I teach this in regular statistics, this takes me like a whole night. We just jam through it and we go, hey, by the way, this is called probability distribution. I'll try to be kind when I pick your problems. Sorry about this, but I got odds. Might set a record night. Try to keep this done. So there's a thing called odds for. Sorry, I can't even talk straight. Odds for an event A. So when you go to the track, not that you go to the track, but you say the odds are 2 chances for a win and 5 chances for a loss. And this is the win-loss. And if somebody wants to let me see how do I do this? I think the book did a terrible job of explaining it just now, so I'm a little stumped here. What it is, it's the probability of this event, then, is you take the wins, oh, there we go, over the wins plus the losses. The book had a different way of explaining it, so we definitely are doing a lot better job than the book. So the probability of the event is 2 out of 7. So odds and probability seem the same, but they're not. They're very similar. So that odds for an event, let's say, are 2 to 5, and it's wins to losses. Now, let me see if I can do it the other way. So if I know the probability of an event, I don't know why I did it that way. That's kind of dumb. The probability of an event is 4/9, or, well, I want to go with 4/9. This is the wins over the wins plus the losses. So if you want to come up with odds for, and I know that's weird when you say odds for, they are wins for, but how many losses do we have? Well, if this is wins plus losses, it's 5. Odds for. Now, if somebody says odds against, you just take the odds for and reverse the numbers. So it's 5 to 4. Therefore, the probability against has a new formula. It's losses over losses plus wins. So we know there's 5 losses to 4 wins, but the probability against is the number of losses over the losses plus wins. Now, what the book is saying is the odds for event A is equal to the probability of A divided by the probability of not A. So, here's what we're going to do. We're going to try to figure out what the book is doing to us. Because I've given this lecture a ton of times, and they gave me something I'm not used to. So what we're going to do is find this example. What are the odds for getting 2 heads when tossing 2 coins together? Okay, so we're going to toss 2 coins. Head, tails. Head, tails. Head, tails. And you get head, 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 tail, tail, head, tail, tail. And they're asking for what is the probability, what is the odds for 2 heads. So it's the probability of 2 heads divided by the probability of not 2 heads. And they're saying odds for is actually a number. Now the probability of 2 heads is 1 out of 4. The probability of not 2 heads is 3 out of 4. And the way that works mathematically is you copy dot flop And they say the odds for are two heads. Here's where they suck, because this isn't real life. Here's what's going on. This is the wins, this is the losses. So all they're really saying, and they kind of mess it up, because in real life you say 1, 2, 3. So all they're really saying is that this answer can be transformed into real life stuff if you go 1:3. But then again, it gives us some pretty good power to, it's even more power than what I gave you. Because I gave you some real good stuff, and this will help you, no problem. But you got to understand that the odds for in our textbook, they don't use this lingo. They say it's 2/5, which really means nothing to me, because that's not the way real world works. You go to the track and they say it's this ratio. And then the odds against, well, the odds against is this number, 5/4. But it means nothing to me, because 5 do 4 means something to me. A number for odds against, 5/4, is kind of pointless. Really hate how they did that. So finally, the book says odds against A, and they go, it's the probability of not A over the probability of A. So it's the reciprocal of the probability of odds for. So we know it's 3-1. But what they really mean, it's losses to wins. And what they really mean, if in real life, it's 3 losses to 1 win. If you're at the track, they don't do odds against. They do odds for. So I hope I didn't confuse you. I might have. But I'm telling you, I got everything there you need to have. I should probably try another one. So in a horse race, I feel bad that I'm going long. In a horse race, the odds for, and now the book, that's R, A-R-E, are 7-2. They try to make up for their terrible explanation. That's wins to losses. Now, if you bet $10 and Blue Moon wins, how much do you gain? Boy, so let's think about this. So you bet $2, and so for each 7-2, that means that for each $2 you bet on Blue Moon, you gain 7 if you win. So a bet of $10 is equivalent to $2 bets. So you gain 5 times 7 is 35. Oh my God, they make this so hard. All right, so let's convert this first, just for fun. What's the probability for? So that's wins over wins plus losses, and that's 7 wins over 9. So 7/9 is the probability, or the percentage chance, but you're not supposed to say that, that the horse will win. So it's quite high. 7/9 is, this is gonna most likely happen. Now, what the book is doing is they're saying, with respect to money, for a $2 bet on Blue Moon, you gain 7. So it's for a $2 bet, you gain 7. I just don't like how they're doing that. So you assume the loss. It's a $2 bet, you gain 7, and they're saying it's happening 5 times. So they're going to give you $35 plus you can get your $10 back. So interesting way to look at it, that is for sure. So let me see if I can explain it better on the fly here. Yeah, I needed a second. Okay, when I go to the track, not that I go to the track a lot, but I must say I'm, from Wisconsin, grew up gambling, but I always like take the odds for, which is always true at the track, and what I do is I just try to get this side to be 1. So I go divided by 2 divided by 2 is the same ratio. So if you put $10 in, it's like 10 $1 bets, then you go times 10. Way easier to explain than what the book did. So you put your $10 down, in the booth, but the payout is going to be $35 on a $10 bet. So you're going to get your $10 back, and you're also going to get your 35. But once again, the secret is to take the loss number down to 1, and then whatever your bet is, do what I did, and you figure it out. The book, boy, they missed the boat on that one. I have a feeling I'm going to be doing a lot of homework on this, but anyway, we're done. That was a long one. Probably could have did it quicker, but there you go. Good luck.